Hi, everyone. Today we're going to be talking about the thermal aspects of the building enclosure, focusing on the performance criteria which make the ceilings, floors, walls, and windows perform so that comfort within the building can be controlled in an energy efficient manner. So this is about me, and when you get the slide deck, you can look at it. We're going to do a brief review of what a building enclosure's function is, and then we'll get into the performance factors for each of the building enclosure components: the ceilings, walls, windows, floors, and air sealing of the enclosure to limit the loss of our conditioned air and the introduction of unconditioned, dirty, contaminated, polluted air. We'll spend a little time looking at 2 case studies, and then we'll summarize the important points of the presentation. So starting with enclosure basics and a little bit of review from the previous high performance enclosure course. So 15 years ago, we used to talk about the building envelope or shell, and many professionals in the industry still use those terms. But somewhere around 7 years ago or so, it was kind of collectively decided that enclosure was a much better descriptor of the parts of a building that are meant to shelter us from the outside elements and contain the conditioned air. So you'll hear me talking about the building enclosure, but those other terms, no matter what climate, are referring to the structure that separates us from the outdoors, made up of the ceilings, walls, windows, doors, and floors. This is the third class in the High Performance Fundamentals Certification Series. And in class 2, the role of building science in high performance buildings, the instructor went into all of the elements the building enclosure must control, which are water, water vapor, airflow, and heat flow. And overall, the building industry does an okay job controlling water and water vapor. Builders have come to realize that they are liable for water and water vapor issues within the first 10 years of a building's life, whether that's a leaky window or other water leak or a condensation problem in, say, a bathroom because it's not ventilated well enough. So because of these things, builders have become pretty good at attempting to keep water problems from occurring. Unfortunately, the builder is not required to truly take responsibility for the second two, airflow and heat flow. And at this point in California, there are no actual standards or specific requirements for airflow or heat flow through our buildings. Blower door testing, which is the test that quantifies airflow through a building enclosure, is not required by California's building code or our energy code. Nor is the inspection on the installation quality of the insulation mandatory under California's energy efficiency performance approach, which is what the vast majority of homes are built using. So the lack of these 2 requirements results in the construction industry not being accountable and therefore doing a poor job controlling airflow and heat flow through the building enclosure. And this building code deficiency manifests in things like the inability to manage indoor air quality and poor thermal comfort, which in turn drives up heating and cooling costs for the occupants. The instructor for class 2 went into detail about the 3 methods of heat transfer. I'll be spending quite a bit of time talking about convective heat transfer, which is heat transfer caused by the movement of fluids. And air has mass, and it is a fluid. It's the primary fluid we're concerned about with regard to a building's energy performance. Over most of the building enclosure, radiant heat transfer is orders of magnitude less than convective heat transfer. The equation for BTUs per hour of radiant heat transfer is this equation down here, the bottom part of our slide. The Q in the equation is mathematically related to this really small constant, which is like 8 zeros and then 1 7. And we take that constant times the area, which is the A in the equation, times the temperature difference, which is the T, to the temperature difference to the fourth power between the two bodies radiating to each other. So that just shows you in residential buildings, because that constant is so small and the temperature differences basically are so small, radiant heat transfer has only a minimal effect across the building enclosure, with the exception of our roof assemblies. Across a roof assembly, the sun provides enough radiant heat transfer that radiation is a true issue through the roof sheathing. So I'm going to talk just a moment here about the learning process. When we're learning something new, we're often not going to grasp it, even what's considered maybe a fundamental concept. The first possibly few times through hearing about it and having it explained to us. So, not all concepts are simple to understand immediately. And the way heat and air flow through buildings it's both complicated and nuanced. So the first time you're being taught a new concept, it may go over your head, and that's to be expected. We have to be exposed to some concepts numerous times before they're finally click into place in our brains. So some of the concepts that I'm going to be presenting today should be considered, that first confusing exposure to something that's complicated and nuanced. So if you manage to make it through this entire presentation without some lingering questions, then that's great. But, really this presentation was too basic for you. You're ready to move on to some of the more advanced concepts. So that being said, this diagram contains one of those fundamental but often difficult to grasp concepts. It's a graphic presentation of the temperature profile across a wall assembly. This is a sectional diagram drawing of a wall from the exterior to the interior. We've got the exterior siding on the left. The wall has sheathing behind the siding. The wall's filled with insulation between the wall studs, and then there's the interior surface of the wall, which is a gypsum board. And what I really want you to take note of is that there is actually an air film on both the exterior and the interior surfaces of the wall. On both the outer and inner surface of the wall, there is a very thin layer of air molecules that lies infinitely close to the physical surface of the wall. And this air film provides a really significant resistance to heat transfer. And we can calculate that resistance to heat transfer and give it an R value. So an R value, for any of you who aren't familiar with the concept, is a number given to the resistance to heat transfer of a material or assembly of materials. And the higher the R value, the better that material or assembly is at resisting or slowing the transfer of heat. The values are different on the outside and the inside of the wall because the resistance to heat transfer is a function of a still air film. And on the exterior, the still air film tends to be thinner because it's constantly getting disturbed by wind. So for this reason, when we're working with the concept of still air films or modeling them as part of an R value of a wall assembly, there is an assumed 15-mile-per-hour wind across the outside of the building, which reduces the thickness and therefore the exterior R value of the still air film on the exterior to a 0.17. Inside the house, any air movement effect to the still air film is negligible. So we get the full impact of the resistance to heat transfer of that air film, and that's an R value of 0.68. And just to give you some perspective on how significant that is, drywall, or the gypsum board, which is typically a half of an inch thick on our interior walls, has an R value of only 0.45. So the interior still air film actually provides a greater resistance to heat flow than the drywall does. So I'm priming you with this concept now in this section about heat transfer. Later in the presentation, I'll be incorporating the R value of the still air films when calculating the effective R value of a wall assembly. These percentages of heat loss by building enclosure component come from the California Energy Commission's computer model using the CBEC residential software. This modeling is for new energy efficient homes. And you can see that ceilings, ducts, and walls are all relatively small percentages. Buildings lose more heat through the slab edge, the windows, and the most heat loss happens through air infiltration, according to the CBEC modeling. And note that these percentages are for heat loss, so these are heating season percentages. Things vary a bit for the cooling season, but this gives us a relative idea of where we should focus our enclosure performance efforts. The magnitude of the various barriers to enclosure performance varies significantly, but the one we always talk about first is architectural complexity, because that's where the most difficult barrier to overcome manifests itself. Sometimes residential buildings are so complex that A, they are excruciatingly difficult to air seal properly, and B, they're extremely hard to insulate, resulting in insulation that's not functioning at its rated R value. When insulation does not perform at its rated R value, we say that it is not performing properly or it's poorly performing. On top of architectural complexity, construction is rife with price pressures. In addition, there is a lack of installer training, and then the fact that no testing is done to determine if an air barrier has actually been created or that the insulation is functioning at its rated R value. All of this makes the creation of high performance enclosures more difficult to achieve. In terms of tackling those barriers to enclosure performance, the only place that architectural complexity can really be addressed is at the design level. Designers need to be made aware of the near impossibility it would be to insulate a turret like this one pictured with curved walls consisting of 2 rows of 2x4s that are 24 inches apart. So if any attention is going to actually be paid to cost, it is near impossible to air seal and insulate this assembly affordably, and price pressures are really a big deal in production housing in particular. So education can help by giving builders the knowledge necessary to figure out how to cost effectively incorporate high performance principles into their building practices. Then there's no testing. Excuse me. With no testing, leaky enclosures and insulation that doesn't perform well will go undiscovered. Contractors need to take responsibility for airflow and heat flow through the enclosures they're building. They need to inspect the performance of the insulation and own the basic test equipment so that they can test their work in order to truly know if their building practices are working in regards to airflow and heat flow. And training is ultimately why we're here today, to provide all of you with some. A home performance contractor I know told me how one day he was in a new construction home and he got to hear a new insulation hire get trained for the job at hand. They were installing Owens Corning fiberglass bats, which happened to be pink. And the experienced installer turned to that new first day installer. He pointed at the walls and he said, "Make them pink." And so with just 3 words, a new insulation installer was born. So I'm hoping that by the end of today's presentation, you will all have learned why that training instruction does not properly serve buildings nor the occupants. When a question came in if there's grant programs to purchase test equipment, and I personally am not aware of any grant programs to help you purchase your test equipment. So Ian or any resources that are out there, can be put out to this person who asked that. There's many tests which need to be performed to not only assist us in our endeavor of creating a high performance building, but also to inform us and document that we have really achieved our goals for the building. And the blower door is the main diagnostic tool for the building enclosure. And with the blower door, we can quantify the amount of air leakage through the building enclosure. It can be used to assist us in locating air leakage locations, measuring the effectiveness of air sealing efforts, and calculating how quickly the air in our buildings changes over per hour. 2 days ago, I presented my blower door basics and beyond webinar where using the blower door is explained in great detail. So take a look for that webinar on the 3C Ren website if you're interested in learning a bit more about the blower door testing. This table graph chart is from a research project performed for the California Energy Commission's Public Interest Energy Research Program. Each bar represents a single home's total blower door test result, with the additional zonal information of how much of that leakage was between the attic and the conditioned space, the garage and the conditioned space, and how much was from other leaks in the rest of the enclosure, such as walls, fenestrations, and crawl space or slab edge. On the left is the blower door result expressed in air changes per hour at a test pressure of 50 pascals. That's that ACH 50. As you can see, the results are really all over the map, even though all of these homes were built to the exact same building code specifications. And this is what happens when no testing is required, when no targets are set and no commissioning testing is done by the builders to inform them how well or how poorly their buildings are performing. The letter grades on the right were attached to give all of you an idea of what would be considered a good house through a house that should be considered an unmitigated failure in regard to air leakage, which, if you remember from earlier, causes thermal comfort issues, inability to control air quality, and higher energy costs. In new construction, builders should be targeting 1 ACH 50 or less. And that's when we give an A grade, is for 1 ACH 50 or less. When retrofitting a house, contractors should target a maximum of 3 ACH 50. So in a retrofit, we can't always expect to do better than a 3 ACH, but that's where our target should be. These are the universal performance factors for building enclosures. First, an air barrier is needed that is continuous and substantially airtight. The second criteria is the insulation itself, which is the thermal layer. It needs to be in complete and continuous contact with the air barrier, which means there cannot be what has been dubbed any gaps, voids, or compression of the thermal layer. So basically, there truly needs to be no defects in the way the insulation is installed. This picture is overall a really good installation, but it could be better, and we can see that there are some flaws. We can see that the outer piece of insulation that the model is holding has been cut around the wall electrical outlet there and delaminated is what we called it when it's pulled apart, so that insulation goes behind the wiring to be in contact with the exterior air barrier and then fits around in front of the wiring so that insulation will also be in contact with the drywall air barrier once the drywall is installed. But if you look closely, that bat was not delaminated behind the electrical box, and there are gaps around the electrical box in that back piece of insulation. And once the upper delaminated piece is fit in place, those defects are going to be completely hidden behind very nice looking insulation, but those hidden defects will degrade the effectiveness of the insulation in that stud bay. Heat will travel much more quickly through those gaps and behind that electrical box. And if there are similar issues, say around all of the electrical boxes, that adds up. And then there are, these other gaps like under the window, which add additional surface area of poor R value. The gaps under the window would be, those would actually be very visible with infrared thermography. The heat transfer that we are able to see with the infrared will pick those areas up quite easily. Since that's about the only thing, resisting heat transfer is the exterior air films there. But bats are really difficult to install perfectly, and extreme care must be taken with an eye for all the critical details. And I'm going to go over lots of examples in today's presentation. This is another topic covered in class 2 of the series, the importance of building tight and ventilating right. Build tight and ventilate right is the mantra for high performance homes. Houses do not need to breathe. People need to breathe, and people breathe by way of properly installed ventilation systems. If we allow intentional holes in the building enclosure so that houses can so-called breathe, we end up with highly variable, uncontrollable conditions within our homes. And this happens because the natural driving forces of wind pressure, the stack effect, and mechanical effect all vary. Um, on a cold day, the stack effect is at its maximum magnitude, and this causes air changes per hour to be too high and air temperatures in the house to become stratified. We end up with cold feet and hot heads, while on a mild windless day, when there is very little stack effect, we get near zero natural ventilation and a very stuffy house. And then on a windy day, we get excessive infiltration, which also creates an uncomfortable home. But when we build tight and mechanically ventilate properly, then when the wind pressure varies on a windy day, we still have just the right amount of ventilation without excessive air leakage. Stack effect is lessened to the degree that enables us to eliminate indoor air stratification with properly installed mechanical conditioning systems while still providing adequate ventilation. Mechanical equipment in our homes often depressurize the house, whether it's through supply duct leakage, bathroom exhaust fans, clothes dryers, or kitchen range hoods. All of these mechanicals can depressurize a house. The degree to which each depressurizes the house varies tremendously. In addition, they have a cumulative depressurizing effect when more than one is operating simultaneously. The mechanical effect must not be ignored, and it needs to be dealt with as we build tight and ventilate right. The installation quality of the thermal layer, the building insulation, is far more important than the insulation specified R value. The upper picture is well insulated R19 bats in a wall. When the interior drywall is installed, the insulation's paper facing will be in complete and continuous contact with the drywall, and the bats are fitted completely in each stud bay. Therefore, the wall will perform well. The lower picture is R30 bats installed poorly in a ceiling. When the ceiling drywall is installed, neither the unfaced bats nor the faced bats will be making much contact with the drywall. This will severely degrade the thermal performance of the insulation. This assembly will perform at maybe 50% or less than its rated value. Throughout this presentation, you'll be continually reminded of the performance factors, so much so that I hope you'll find yourself reciting them in your sleep. So here we go. Continuous and airtight air barrier, insulation in full contact with the air barrier with no defects in the installation. And before we move on, let's talk about these gaps and voids, which you're going to hear a bunch about. The actual calling out of whether a defect is a gap or a void is really completely irrelevant. You don't need to come away from this presentation being able to distinguish a gap from a void. Those two words are mere terminology adopted for the HERS raters when they're out doing their quality inspections of insulation installations, the QII inspection. The point is not the term used for a particular defect in the installation. The goal of today's presentation is for you to begin to recognize well-installed insulation versus poorly installed insulation, and to understand that well-installed insulation will perform at its rated R value, whereas the R value of poorly installed insulation diminishes very quickly with seemingly small flaws, hence the mantra. Installation quality is more important than R value. We'll begin with ceilings, which account for about 9% of the enclosure's heat loss with regards to insulation performance. With regards to air leakage, ceilings account for about 51% of the enclosure's total air leakage. Here are the performance factors that are specific to ceilings. Number 1, is we need a continuous and airtight air barrier. The air barrier of the building enclosure is typically the ceiling drywall. Drywall is inherently airtight and continuous, except where it is interrupted by interior partition walls. And this interruption, unfortunately, greatly complicates the creation of an airtight air barrier at the ceiling. And our description of air barriers needs to be expanded when we're talking about air permeable insulation. There is the primary air barrier defining the conditioned space from the unconditioned space, but there are other air barriers within our buildings that air permeable insulation needs to be in contact with to stop convective heat transfer. These other air barriers are building components such as the studs in the stud bays, the top and bottom plates, the interior drywall, and ceiling joists. Those are all examples of air barriers that create cavities in which air permeable insulation can be installed and stop convective heat transfer as long as the insulation is actually in continuous contact with all the air barriers surrounding the cavity the insulation is in. The number of air barriers insulation must be in contact with is different depending upon the building assembly in which it's being installed. So as we go through each assembly, I'll tell you how many air barriers each assembly has that the insulation must be in contact with. There are 5 sides to the air barrier of ceiling insulation. The first air barrier would be the ceiling drywall, which is in this picture, has not yet been installed. The attic joists on each side of the insulation are the second and third air barriers. And then at each end of the insulation, there needs to be an air barrier. And in this picture, we can see the fourth side of this upper bat, which I might call the bottom of that bat. And the same framing member is the fifth side or top side of the lower bat. So that takes care of performance factor number 1. Performance factors number 2 and 3 are the universal performance factors for all insulation installations. The entirety of the insulation must be touching the appropriate air barriers, meaning the insulation needs to actually be touching in full contact with the ceiling drywall, the joists side to side, and the ends top to bottom with no gaps, no voids, and no compression of the insulation. So what do you think? Will this insulation be in contact with the ceiling drywall when the drywall is finally installed? Anybody can quickly type in a yes or no. But I'm going to keep moving as you're potentially typing that in. It won't be. This is a photo of R38 bats installed in a truss ceiling. Trusses are really difficult for an untrained workforce to insulate properly. There was no comprehension of where the insulation should be placed in order for it to be in contact with the yet to be installed ceiling drywall air barrier. There's virtually nowhere where for this insulation that it'll be in contact with the drywall once it's installed. I mean, look at this area. The insulation bat's like 8 inches above where the drywall will eventually be. The R value of this area, which really only consists of the drywall and those still air films I taught you about earlier, is going to end up being only about R1.5. A lot of heat is going to conduct through the drywall and end up inside the space between the drywall and the building insulation. And then convective heat transfer is going to carry that heat up into the vented attic through openings that are like here and here and everywhere else. There's even some at this overlap over here. So this area of insulation that will be touching the drywall a little bit will not perform at R38 either. It may achieve about an R3 because of the convective heat flow up through those openings and up into the attic. All in all, the overall thermal performance of this assembly is more like an R3 to an R5, even though these are R38 bats. Much, much, much below what's actually assumed. This is representative of how modeling of an assembly in California's energy code compliant software ends up predicting compliance, when in actuality, this assembly is a complete failure.
Judy, we have a quick
Yeah, I was
question in the chat.
just seeing that. When using closed cell foam and sealing assemblies, the foam does not necessarily fill the entire void to achieve the R value, nor desirable due to cost. Is the gap void problematic? Well, voids are always problematic. Gaps are always problematic. So whether it's spray foam or air permeable insulation, if the insulation is not creating, is not filling the cavity, it's a problem. And when spray foam isn't potentially sticking to an assembly properly, or not filling properly, or not at its proper number of inches to achieve its R value, it's just about as easy to do a bad job with closed cell spray foam as it is with bats. So this is just a different attic, but it has the same issues. The insulation is under a mechanical equipment platform. You can see the equipment up here. The insulation itself is not going to be in contact with the ceiling drywall when the ceiling drywall is finally installed, except kind of in some random places. And this is going to allow that heat that conducts through the ceiling drywall to then move convectively up around the edges of the platform and then be lost into the attic. This is an example of a fairly well-installed attic insulation. And I'm sure somebody's going to be curious. These are the Ultra Touch denim bats, which are very difficult to work with. In order to really determine, though, if there are any hidden issues, we need to lift some of those bats up a bit to take a look at things like whether the bats have been delaminated around electrical conduit or gas lines or plumbing pipes. This electrical conduit down here in the bottom is compressing that bat. So that's an issue. And then, this other bat was moved by an HVAC installer when they were installing a new duct, and then that individual didn't properly replace the bat, which in this instance really should have been the HVAC company's responsibility, since they're the ones that moved it to put their duct in. But for whatever reasons, price pressure, lack of training, this trade, whose first concern should really be a comfortable home, left this home in a worse condition than it was prior to their duct installation. This is an example of an architectural trend that began in about the mid-90s and that lasted through about 2008. And what's unique about it is the complexity it created for insulators. Architects frequently get caught up in their artistic vision and do not give any thought to how difficult the intricacies of their vision make for defining the primary air barrier of the building enclosure. So where should the air barrier be defined in this picture? Should it follow the ceiling line, or should it drop down over here and above these arches? Either one would work, but the decision has to be consciously made, and the air barrier has to be created following the chosen path. And some trade or individual on every job site really needs to be responsible for air sealing if we hope to create high-performing buildings. At this point in time, there's not any trade that takes responsibility for creating and maintaining the enclosure's air barrier throughout the construction process. A detail showing the primary air barrier really needs to be included in every plan set. I'm gonna just go back to Hank's question. So, Hank, you're saying when using closed cell foam in ceiling assemblies, the foam does not necessarily fill the entire void. So a void is not the empty space of a cavity. So, so that is so that's what I was realizing. I didn't understand your question because of your use of the word void. Closed cell foam. So it's not that we're absolutely in a ceiling assembly, which is what we're talking about right now. The thickness of the insulation could end up above the joist, or potentially, if you're not using as much R value, then the thickness of the insulation might not go to the top of the joist. So that's not the void. That is about the thickness of the insulation and its R value. So the R value of spray foam is a bit higher than bats, and so you don't need as many inches. But when spray foam doesn't stick appropriately to the surface, to that primary air barrier, or to the side air barriers, the joists, or the end-to-end air barrier, which it often does not, then there will be a degradation of the R value of that spray foamed assembly, and it's not going to achieve its R value. So in that sense, are gaps and voids problematic? Well, yeah, gaps and voids are problematic because they truly are what I would call a void. They're not, the insulation is missing because it didn't stick, or for some reason it wasn't sprayed there. The fact that the thickness is not the same necessarily, yeah, the lifts don't end up being the same, but that also means that the R value of those lifts is varying with spray foam insulation. It's not a silver bullet, and it's not necessarily it's definitely not easy to install properly in the field. And it does have to be a particular number of inches to achieve its R value. So when it's not uniform, when it's not a uniform thickness, you're getting different R values at different spots of that spray foam. So this presentation is not about any particular insulation in particular. It's about the assemblies and the performance factors. And so I'm going to keep moving on and not focus on a particular insulation. Here, this is one of the most overlooked deficiencies in the creation of the primary air barrier, referring to the air barrier that's meant to keep the conditioned air inside the house and prevent unconditioned air from entering the house. This is an interior wall cavity, which means it should be completely inside the thermal enclosure, the conditioned space, but there's an opening at the top of the wall, which is great for the electrician. He, she, they will be able to run wires into the wall system without having to drill any holes through the top plate. But for the air barrier, it's a complete disaster. If that space is left open when the home is finished, this wall will forever be connected to the attic, which I will remind you is outside the conditioned space. In the winter, heated air from inside the house will rise up and escape into the attic, making the heating equipment work harder. And then in the summer, superheated attic air will wash down inside that wall cavity and cause the air conditioner to work harder to cool the house. A convective loop will establish, pulling the unconditioned air into the wall, while conditioned air will escape up into the attic. And this is the type of air leakage pathway that drives stack effect in a house. This is another example of architectural complexity. This is a slab-on-grade residential home with these 3 columns that separate the great room from the kitchen and the breakfast nook. You can walk completely around all of these columns. These 3 big columns and all of their interior drywall should be completely within the interior space. But, are they? Any idea how we figure out whether or not they are? So type in your suggestions. What tests can we do to determine if these columns are within the primary air barrier? Okay, somebody answered blower door. So the blower door is going to help us quantify air leakage. It's not going to necessarily let us tell whether whether these columns in particular are part of the primary air barrier. Thank you for giving that a try. If you've ever seen an infrared picture, infrared is showing us temperature differences, and that is what this area looks like in infrared. And we can see that the center column is filled with cold air. Those darker colors are colder colors, and the leakage path to that interior column is over here to the left. So it's looking like the leakage path from the attic is coming down through here and across and over here. And it's looking like we've actually got an okay air barrier over here from this column. So we've got this indirect path, but this is making all of this attic unconditioned space and communicating with the attic, where it's also communicating with the house, causing all kinds of comfort issues and thermal issues. So this is a huge building defect, and it's quite common, but it rarely ever gets caught because contractors don't have infrared cameras and they don't check their work in infrared. So, okay, so you've witnessed how bats in those previous photos are virtually impossible to install properly in something like a truss attic. It's just too hard to meet the performance criteria of no gaps, no voids, and no compression, as well as being extremely difficult to install. So that they're in complete contact with the drywall. This picture appears to be beautifully installed loose fill fiberglass insulation. So whether it's fiberglass or cellulose, loose fill insulation inherently performs well because by its very nature, it settles around all the obstacles to lay on the ceiling drywall. But the thing is that if you were to ask me if this is a good installation, I would have to say that I don't know. I can't tell. I can't tell if it's the right depth since the mandatory insulation rulers are missing. I have no way of knowing if there's continuity of the air barrier below the insulation. I don't know if this insulation was blown on top of poorly installed bats or if it's just this blown in insulation in the attic. So once attic insulation is installed, the only way that we really have to determine if it's performing properly is using an infrared camera and a blower door simultaneously, because the blower door helps us to see those temperature differences by moving the air from, say, the attic or crawl space through those indirect air leakage pathways. So anyway, I hope that you are beginning to recognize the importance of testing and the value of owning that blower door and an infrared camera. This is exactly the same issue as the previous photo. This is the stick frame newer attic. Visually, this looks like a beautiful loose fill cellulose, but again, there's no way of knowing whether or not the air barrier underneath this insulation is properly sealed and therefore continuous. And once again, there's no insulation rulers to show us the depth of the insulation. So the R value of loose fill insulation is determined by inch and by how densely it is put into the assembly. This is a picture of the mandatory insulation rulers I've been saying were missing in those previous photos. And there they are for the installers to blow the insulation into the correct depth and in turn show us, an inspector, the depth of the insulation and therefore the installed R value. Now here, someone's done an excellent job of cutting and fitting fiberglass bats around the bottom truss cord, yet this would still fail our performance criteria. So see right here where the bat's compressed up and around the electrical box. This area where the insulation will not be in contact with the air barrier once the air barrier installed is a void. California State's Energy Code has a section called QII, Quality Insulation Installation, that outlines the requirements for how insulation needs to be installed to function properly. QII actually allows for small voids that are less than 3/4 of an inch deep on the front or back of a bat, as long as the total void area is not over 10% of the bat's surface. So even though this looks quite nice, this void is greater than 3/4 of an inch deep, so it does not pass the performance criteria outlined in QII. And the same problem exists right over here, and there are other places as well in this picture where that problem exists. The continuity of the air barrier in a ceiling assembly gets really complicated due to architectural complexity. This is a big interstitial cavity. It's a void space that the architect just didn't use, and it's not properly fire blocked. And when we look at this picture, we look up and we see that four-sided sheet of OSB, which makes it appear as if the fire blocking was done. And since this past inspection, before this picture was taken, the building inspector apparently thought the fire blocking was complete and correct. But when we look a little bit closer, we notice that the ceiling level in the hall bath on the right over here is dropped about a foot below the standard truss ceiling level. So that means this area is completely open to the attic. So though the top of this interstitial cavity has a fire stop, and the fire stop, the fire could still just make this little zigzag and move straight up into the attic. And the master bedroom in this floor plan also has a lower ceiling over the vanities. And this area, again, is completely open to the attic. Between the master bathroom and the master bedroom, there is actually an arch. So there's an area here completely open to the attic. So even though this is a life and safety violation and building inspectors try to catch all these, definitely between the mid-90s and 2000s, on average, they missed at least a dozen on every house built. And this missing fire block is what insulation subcontractors rely on as the air barrier. So they will install a bunch of insulation and it could end up looking really good from above. But because of all these missing fire blocks, we'll have very poor thermal performance, especially during the winter time because of the openings between these interior walls and the vented attic. This is more of exactly the same, a foot thick wall completely open to the attic. It's always a warning sign for insulators when the electrician does not have to drill holes to get between a wall cavity and the attic. This should tell them something isn't properly fire blocked. In retrofits, this is how we catch these deficiencies. Here's a big section of interior wall with tall ceilings, and it's all completely open to the attic. This is a wintertime picture, and by depressurizing the house slightly with a blower door and looking at interior walls with an infrared camera, we find these big sections of interior wall assemblies that are all open to the attic because of improperly installed or completely missing fire blocks. And what we're seeing is the cold air from the attic being pulled down into the walls with the blower door depressurizing the house. And this is what would occur in this wall system if the house became depressurized through natural driving forces or through the mechanical effect. This is a drop ceiling above an entry closet. And what we're looking at here is the backside of uninsulated drywall. Often there's no fire block here between the lower part of the wall section, which is the ceiling plane of the closet. Not only is the upper part of the wall section completely uninsulated, but the insulation at the upper ceiling level drops to 0 depth. So these wall cavities are found to be open, which increases the heat loss at the interior walls. This is a wintertime picture of cold air leaking down into an interior wall, as well as the uninsulated drywall up higher. So this is kind of what that last picture would look like in infrared. It's a similar assembly. This is typically the easiest way to fix drop ceilings, interstitial cavities, and small ceiling plane changes. This technique is called block and seal. You bring the air barrier up to the level of the rest of the ceiling plane, making the interior of the soffit part of the conditioned space. The opening gets blocked with an air barrier material, which can be plywood, it can be OSB, drywall, rigid foam board, any material that is impermeable to air. It can be toe-nailed into place or secured in some other way, and then all the edges are sealed to the surrounding drywall or surface with an appropriate air sealing material, which can be a one-part low expanding spray foam, mastic, air sealing tapes, a fluid applied sealant. There's a myriad choice of materials. So the performance factors for ceilings: a continuous and airtight ceiling air barrier. Ceiling drywall is most often where the air barrier is meant to be, and that's where it needs to be in any building with a vented attic. The problem is the inherently airtight drywall is continually interrupted by top plates and recessed lightings, electrical junction boxes, electrical wiring, plumbing, etc. And this makes the creation of a continuous and airtight barrier complicated. Insulation must be in contact with the air barrier on 5 sides to achieve its rated R value. Batt insulation is near impossible to cut and fit around truss cords and web stiffeners and all the other obstructions, including electrical wires and conduit, other cables, plumbing pipes. It takes very careful attention to detail to install batt insulation products well. Loose fill insulations are inherently higher performance because the loose fill can be easily blown under and around and over the top of the typical obstructions in an attic. And loose fill insulations are fairly immune from the issue of gaps and voids, as they will settle into and fill all those small spaces, which batt insulation can only bridge unless it is cut and fitted like a jigsaw puzzle. And it's important that loose fill insulations be installed at the proper density and are not compressed. And typically, if we're using a spray foam insulation, then we're doing it up at the roof deck, not at the ceiling level. And then we're working with an unvented attic rather than a vented attic. So let's move on to walls. These are the performance factors for walls, and there's one significant difference in the performance factors between walls and those of ceilings and floors, and that is number 2. Wall insulation must be in contact with all 6 sides of the cavity, front and back, both sides, top and bottom. Each one of these locations is an air impermeable material. In other words, they're all air barriers, and if they're not, then an air barrier needs to be installed at the missing location. And this is commonly the case with knee walls, which we'll discuss soon. The physical height of the insulation of ceilings and in floor joists can be less than maybe, a foot to 16 inches deep. The driving force for convective heat flow through a blanket of insulation that's only 16 inches tall is fairly negligible, whereas the driving force for convective heat flow in a wall cavity that can be as tall as 10 feet is significant. On average, there's 10 times more convective driving height than convective heat flow in walls as there is for floors and ceilings. And that's the big difference between walls and ceilings and floors. So because of this difference, walls need a substantially airtight wall cavity for the insulation to be installed within. Fibrous insulations do not stop air movement. Air will move right through fibrous insulations just like air moves through a filter. The insulation needs to be in contact with air impermeable materials on all sides in a wall assembly in order to stop convection. And those air barriers stop the air from flowing through the insulation, and this is what enables insulation to do its job, which is slowing the transfer of heat through that heat transfer mechanism called conduction. So often both the wall's exterior sheathing and the interior drywall act as some portion of the building enclosure's air barrier. For wall insulation to perform properly, it needs to be in continuous contact with both of those surfaces, as well as the studs on each side of the cavity, the floor plate, and the top plate or fire stop. And since there are 6 sides in a wall cavity, the insulation must be in contact with all 6 sides in order for there to be no chance of convective heat transfer. So the mantra for insulation installers is the thermal insulation needs to fully fill the cavity side to side, top to bottom, and front to back. Another difference that's more impactful in the performance of walls than in floors or ceilings is the framing factor, which is the amount of wood that interrupts the continuity of the insulation in the wall assembly. So all of the wood in this assembly, at the bottom picture in particular, conducts heat approximately 4 times faster than does our typical insulation materials, whether that be cellulose, fiberglass, denim, spray foam. The more wood there is in a wall, the greater the two thermal problems wood in a wall creates. There's more surface area where heat is conducting rather rapidly between the inside and the outside. And there is physically less space for insulation in the wall system, which lowers the entire wall's overall thermal performance. And then there's the universal installation requirements of no gaps, no voids, no compression of the insulation. The question is asked, what steps need to be taken to prevent loose fill in a vented attic from being blown into snowdrift? So I'm guessing you're actually talking about what we call wind washing, and it's called baffles. We put baffles up so that the air that's coming in through a vented attic actually cannot just blow through the insulation and blow that loose fill away from the exterior of the enclosure and just end up in big piles. And so the baffles are put right at the edge of the top of the exterior top plate, and then they go up so that we have a 1-inch opening gap between the baffle and the roof deck. And so the air comes in through the vent, goes up and goes along the roof deck, which is really what we want that ventilation air to be doing. It should be moving to keep the roof deck cool and that radiant heat transfer moved around rather than just blowing through our insulation. So this picture is a poor installation. There's an empty cavity where the insulation is buckled over. These are all places where where the insulation is not going to end up being in contact with the air barrier. And there's just a lot of problems here with insulation performance. And the reason is that it's difficult to perfectly cut and fit in fiberglass bats to all the irregular cavities in modern, fairly complex exterior walls. Installing bats can be relatively straightforward when the space the bat's going into is the same proportions as the bat is, but expecting bat insulation to be installed properly per the manufacturer's instructions, which in truth is what the performance criteria are, when every piece needs to be cut and fitted individually, that requires an artist rather than an insulation installer who's getting paid by the piece. This is a photo that's actually out of the Energy Commission's energy manual, and the picture is showing an improper installation. There's not any obstructions. The framing is fairly regular. Overall, this insulation appears to be fairly well installed, but it's a complete performance failure, and that's because of the way these bats are all tucked in on the sides in every single stud bay. That along with so the way that ends up being pushed in ends up with these little triangular voids in all four corners, and that allows a convective loop to set up. And so not only does that happen on the front, but the way the bats get pushed in, it happens on the backside as well. So we end up with this convective loop that is bringing the hot interior conditioned air, gets into the wall system, the hot air travels up the wall. It moves through this air permeable insulation at the top, and then as it cools on the outside, it drops down, and a convective loop ends up getting set up within that wall system. And then that just reverses in the summer. So we have problems in the summer and in the winter. And research has shown that even these little triangular void defects decrease the performance of the whole cavity by about 30%. So this seemingly minor installation issue is really a significant defect. Cutting and fitting is really difficult. There's a big plumbing vent in this section with lots of irregular framing. The bats are too wide for the cavities, so the edges are buckled over. This is just a very difficult wall to insulate properly, especially with bats. It can be done if the installers were trained to really understand how their insulation works and to really take care and to be allowed the time to properly install it, to pay attention to all the right details. But we don't give them that expectation, and we don't give them the time needed for these complicated assemblies to get done correctly. This is a picture showing a wiring obstruction, which is very common in walls. And here the installers put one bat in front of the wire in one bay and the next bat behind it. And what really needed to happen was to make sure that the insulation gets pulled apart, delaminated, as I said, it's called, with enough insulation behind the wire, just the absolute right amount to fit behind the wire and that exterior air barrier, and then for the rest to be folded up in front of that wire and to be in contact with the drywall once the drywall is put up. So there are other ways to deal with this issue, but in practice, the builder, needs to incorporate just the right techniques. And that technique could be, what if we removed the obstacle and placed it someplace else? And so you'll see some pictures of that in just a moment. But first, let me show you an infrared picture of a wire obstruction like that, what it might look like in infrared. So in this image, there's an air leak at this electrical outlet. And because the wire going to the outlet is compressing the insulation, a void is created between the drywall air barrier and the insulation. So along that wire path, the insulation is literally physically unable to stop conductive heat transfer, and it's creating cold spots in the wall assembly. So this is a solution that a very thoughtful builder came up with to avoid the possibility of wiring causing thermal problems in the wall assembly. Before he unstraps a unit of studs, he cuts a V-notch or he drills a hole down through the bottom of the 2x6s. And then the electrical wiring is run cleanly across the bottom plate, so it's no longer an obstacle that the building insulation must be fitted around. Unfortunately, when different trades are involved in the solution, it's what we call misaligned interests. Is it the framer that should be cutting, that V-notch or those holes? Should the electrician have to do it after those studs are already up? Who takes responsibility and who charges for that, and whose time and money does this fall under? So the trades unfortunately seldom work together by agreement or even by expectation set by, say, the general contractor. So who takes responsibility? Should the framer, should the electrician, but a technique like this will drastically improve the building's thermal performance while making it easier to create the thermal boundary of the building. So looking at framing factor, this is the amount of framing that's in an assembly. And if we were to count all if we count the cripple stud, and all the studs, there are 10 2x4s all side by side in this photo. And if you take a look at the house across the street, this house, that's what the house we're looking at, that's the exterior basically of the house that we're looking at. That's the exact same house across the street. So we're looking through the window in the gable end there. And so these 10 2x4s, they're on a gable end. This is not a weight-bearing wall, but for some reason, somebody thought that they needed 10 2x4s to hold something up. And this is an older picture. So that was a little bit of an older picture. This is a very recent picture of a home being built in the Sacramento area. And here there's 5 framing members around every single window. And in high performance buildings, which I'll show you a few framing techniques here in a minute, we get the framing factor down in the range of 9 to 11%. That means that only 9 to 11% of the exterior walls are solid wood. This house has a 35% framing factor, over 3 times more thermal bridging. Thermal bridges are places in an assembly where heat is rapidly conducted through the assembly. As I mentioned earlier, wood is 4 times more conductive than standard insulation. Sorry, I'm trying to put my headphones in because somebody has decided that it's time to leaf blow outside. So wood is 4 times more conductive than standard insulation. So this house overall has 3 times more thermal bridging through the walls, and that's 4 times more conductive than the insulation that will be installed. And so all of that translates to tremendous extra cost to make the building enclosure actually worse. This, on the other hand, is well thought out simplicity. This Stockton builders employing what's called advanced framing techniques, using a single top plate and a single bottom plate and 24-inch on center stud placement. The windows are sized and they're located so that they don't interrupt the framing layout. The framing factor here is 11%, which means that the wall will be 89% insulation. And visually, you can see how easy it would be to insulate these walls. The framing is so nice and uniform. There's no obstructions for the insulation installers to have to deal with. This is the builder who drills the holes at the bottom of the studs for the wiring to run through. So these walls will easily get a near perfect insulation installation, even if the builder does choose to use fiberglass bats. And fiberglass bats are, they're perfectly good insulation, and they're the lowest cost insulation available, and they're very well suited for uniformly framed cavities that are about the same size as the bats produced by the manufacturers are. So when that's not the case, they're very difficult to install. This building in Mount Shasta also used advanced framing techniques. He used 2x8s. It's a triplex, and each unit is 1,000 square feet, and it took only 1 unit of lumber to frame this entire 3,000 square foot building because he used the advanced framing technique. This is what the installed insulation looked like in the Mount Shasta building prior to the interior drywall. And you can see that it's near perfect. This is not advanced framing, but it's still a really good installation job. It would pass all of the performance criteria. This is the first floor and the floor joists of a 2-story house. This installation was done by the insulation installers of the Mount Shasta house. So this is spray applied cellulose insulation. And this is the installation method that's the most immune to poor installation quality. It's close to impossible for this insulation to be installed poorly. There is a bit of a learning curve to get the spray right, and this insulation will literally just fall out of the cavity when the mix isn't right. So it's quite clear whether you got it right or not. If you manage to get the insulation in the walls, sticks, it stays, and it's shaved down and it stays in the walls, you've got basically a perfect installation of a loose fill. This is actually a loose fill spray applied insulation. This is spray applied fiberglass, and the last one was cellulose. This is the Johns Mansfield spider system, and it has 2 advantages over the spray applied cellulose. It can be used overhead on slope ceilings, and it doesn't take as long to dry. So these 2 systems are the most immune to insulation defect. Another method is loose fill behind fabric. It's not quite as good as the previous 2 methods, but you have to get the density right as well. But it still is more immune to insulation defect than bats are. Attic knee walls are kind of a special case. They're a very difficult wall to do. A knee wall is when we have like a raised ceiling in one room, but we've got a lowered ceiling in another room. So there is a wall that is adjacent to attic space on one side and adjacent to conditioned space on the other side. This picture from the California Energy Commission manual says the air barrier is to be placed with that arrow here. So our knee walls typically in attics do not have that sixth side to their air barrier, and it needs to be there for the insulation to actually perform well. If there's only bare insulation on that one side, there's nothing to impede air movement through the insulation or anything preventing convective currents moving around the insulation. So when we look at an attic knee wall in infrared, we typically see at least one section performing horribly, and it's often the case that there's some insulation in the cavity, even though in infrared it looks like the insulation must be completely missing. This is an attic knee wall mid-install. So if the knee wall needs to be framed out, that's done. Air sealing is performed to make the cavity airtight. Then the cavities are insulated per the performance criteria with the insulation of choice, bats, blown-in spray foam, whatever the choice is. In this example, the white fiberglass down here is the cavity insulation. And the attic side is being covered with a product that is smoke and flame spread rated for attic exposure. One product that qualifies as duct wrap. Here, the attic side of this attic knee wall is covered with R8 duct wrap to create the sixth side of the air barrier necessary to make the knee wall perform properly. And sometimes the tops of knee wall cavities are not enclosed. So here, extruded polystyrene foamed into place has been used to enclose the top of the cavity, creating the necessary air barrier at the top for insulation to be in contact with. Let's go through the R-value estimation technique that you can perform in the field to measure the R-value performance of the insulation across a wall assembly. And this test uses the R-value of that interior indoor still air film that I mentioned a few times. And I use this test when I'm doing an energy audit sometimes to figure out what R-value the insulation in a wall is actually performing at. This chart comes in very handy so that we don't actually have to do the math. The only thing we really need to do is take 3 temperature measurements and do a little subtraction. Across the bottom of the chart is the temperature difference between the still interior air film, which is the temperature difference between the inside wall temperature and the inside air temperature. And these are the vertical lines on the chart. Along the right side is the temperature difference across the wall assembly. These are the curved lines on the chart. The left axis is the horizontal lines, which are our value. So if you measure the ambient room temperature with a typical thermometer, you measure the wall temperature with a non-contact IR thermometer, and measure the outside air temperature with your typical thermometer. The first bit of subtraction is the temperature difference between the inside wall and the inside air. And so you'd find that the vertical line on the chart for that value. Next, you figure out the temperature difference between the outside air and the inside wall temperature. So as an example, let's say there's a 2-degree difference between the indoor air temperature and the indoor wall temperature. This is the temperature across that interior still air film. And then let's say there's a 30-degree difference between the outdoor air temperature and the inside wall temperature. And these conditions plot out to about an R12.5 effective wall assembly. So that's how that works. Using that test technique, we can look at the effective R values of 4 different wall assemblies we'd find in an attic knee wall. This is an infrared picture of an attic knee wall demonstration box. So there's 4 little framed sections of attic knee wall. They're about 5 feet wide. The whole box is 5 feet wide, 4 foot tall with 4 stud bays. And each bay is insulated with a different R value of insulation. One of the bays is actually empty. One cavity has an R11 bat in it. Another has an R13 bat, and one has an R19 bat. The area behind the wall is simulated attic conditions. It's heated to 120 degrees so that the outside air temperature we would use that's what we would use in our calculation. And then the front side of the demonstration box is within the room. And, so that when this picture was taken, we were in a 70-degree room. So looking at the image, we would probably make the following assumptions regarding the R value of each cavity. The white hot colors are hot, whereas the darker down to purple colors are cooler temperatures. So knowing that the white hot means lots of heat transfer, the guess would probably be that this is our R0 cavity. On the other end is the coolest one, so that, that cavity is looking really good. So my, assumption would be that that must be the R19 cavity. The one that, doesn't really look quite so good probably is the R13. And then that would leave that, this is the R11 vat. And all of that should probably make some intuitive sense to you. But that's not really the case, right? We didn't install all of these bats well in this cavity. So with our test technique in our chart, we can estimate the actual R value across these 4 assemblies. So this is really what is going on with each of these cavities. The cavity on the right is the one that doesn't have any insulation. The cavity next to that one is actually the R13 bat. The poorly performing cavity is the R19 bat, and the bat on the left performing the best is the R11 bat. So the R11 bat is installed according to the performance criteria, including having an air barrier on the attic side to provide a 6-sided airtight cavity. The R19 and R13 bats have installation defects. And so with our test technique, we can estimate the performing R value across each one of those cavities. The one that's uninsulated is performing at about an R2. So that's the resistance to heat flow of the drywall and the 2 still air films. So the drywall is a 0.45, and the 2 still air films, because this is not a truly exterior wall, the cavity is not affected by a 15-mile-per-hour wind. The 2 still air films are 0.68, and then the drywall is the 0.45. So we end up with R 1.8, so about an R2. The empty cavity still has a little bit of R value. The R13 bat is performing at about an R13. It's a fiberglass bat. It's well installed, but it doesn't have an air barrier on the attic side. And you can see the consequence of that defect by the bleeding of heat at the top and at the bottom. And in the temperature kind of just inconsistency throughout the cavity. The R11 bat is perfectly installed, and it has an estimated R value from our chart of R14, and the R19 bat comes out at an R3. Going back to our chart, there's about a 10-degree measured difference across the still air film of the bay with the R19 bat. And the temperature difference across the whole assembly is 40 degrees. And so we get an R3 estimated performing R value for the cavity with the R19 bat. So that R19 bat, it violates the performance criteria in 2 categories. First of all, it's a bare fiberglass bat on the attic side. Its craft face paper is side stapled in such a way that the paper is not touching the drywall. There's a 1-inch gap between the back of the drywall and the front of the R19 bat. So a convective loop ends up getting set up and going around that bat. So that R3 is the actual performance of the installation for an R19 bat, and that's a huge difference in performance. So little defects are so critical to the assembly's performance. So now you should have a way to estimate performance R value in the field, and you see how that works with this assembly. So back to this picture. This picture looks like a completely missing bat in the knee wall, but when we actually go up and look, we see that there is insulation, but there's an air opening at the top of that. And even though it's loose filled insulation, there is this air opening that is going down along that knee wall. And so convective currents are setting up, and it makes, that little defect is giving us this thermal image where it looks like it's a completely empty bay. So all that insulation is not doing anything. Insulation quality is truly critical. So does this picture portray a correct or incorrect installation of insulation? Put your answer in the chat. Let's move on to windows. Even though windows and doors are intentional holes in the building enclosure, there's still holes in the building enclosure, and we need to pay particular attention to windows. Heat loss is, as estimated by the computer modeling software accounts for 22% of the total heat loss through the enclosure, while heat gain, depending upon the orientation and the quality of the glass, can be much higher. Windows have 4 performance factors: the performance of the glass, the performance of the frame, which impacts the quantity of visible light transmission, and then there's air leakage and exterior shadings, which are really important on retrofitted buildings when windows are not being replaced. As the sun's energy blasts through typical glass windows, over the last 20 years, the glass industry has developed various low solar, low E, spectrally selective glasses, which have helped us reduce this heat gain. New glass products save energy by keeping the sun's energy out in the summer and keeping the heat in during the winter, and we still get adequate visible light. And these coatings have been a game changer for window performance. This meter reads the incident solar energy in BTUs. So right now the window is open. With the window open and the sun at the oblique angle, there's about 240 BTUs per hour per square foot of solar gain through this opening. Now, with the window closed, the solar gain is reduced by almost 60% to only 100 BTUs per hour per square foot. And this is an older retrofit window. The low E coatings on newer window glasses can be significantly better than this. There are a number of ways that windows are rated: the center of glass rating, the glass plus the frame, how much visible light makes it through the glass. There's even an air leakage rating, but what we want to look at is the entire window properties. And this section of a chart on windows is giving us information on a double pane insulating glass unit under 4 different low E types. So we've got none, high solar gain, medium solar gain, low solar gain. The next column tells us the percentage of visible light that makes it through this glass unit, and we don't typically concern ourselves with the visible light transmission, the VLT, as long as it's above 40%. The next grouping is properties of what would be a typical window. Once again, we're not concerned about the visible light transmittance. The factors we're concerned with are the U factor, which is a measure of the conductive heat flow through the window. And for the most part in California, the lower the U factor, the greater reduction in heat gain into our homes. While the second important factor to look at is the solar heat gain coefficient, the SHGC, which represents the fraction of solar radiation that passes through the window. In California, we typically want low solar gain glass, so let's look at this unit's properties. The dual pane insulating glass has 66% visible light transmittance, while the whole assembly had it with a typical vinyl frame still gets 50% visible light transmittance, but with a solar heat gain coefficient value of 0.22, which means that only 22% of the sun's radiant energy is getting through the window, while 78% of the solar radiation is being cut off, helping reduce overall overheating of our homes in the summer. and a U factor of 0.31, which is equivalent to an R value of 3.2, whereas that window without the low E coating has a U factor equivalent to an R 1.8. So the glass industry continues to do better and better with the overall performance of windows. And with advanced windows, we can get U factors of 0.2 and solar heat gain coefficients down in the 0.18 range. The values in this chart are really easy to get for affordable windows, and then we need to spend a little bit more money to get additional performance. To assist in keeping the enclosure's air leakage low, when we build tight and ventilate right, fixed windows are a good option. Fixed windows are quite tight. Hinged or casement style windows can seal well when closed if they have good weather stripping, while slider style windows are the worst performing types of windows in terms of air leakage. And when we're not replacing windows, exterior shades are one of the best options to control solar heat gain in the summer. They're very appropriate for California's sunny and mild climate. With a good enclosure built to high performance standards, we still recommend low solar windows in all cases because it really takes so little solar energy to overheat a house. With high performance enclosures, we're completely moving away from the old passive direct solar heat gain strategy of putting windows on the south side of the house to capture the passive solar heat gain. We just don't need any solar heat gain in a high performance enclosure. And for large glass areas, particularly in retrofit situations, when we're not replacing the glass, the only option is exterior shades. And shade screens work well in all orientations, even south and west facing. Some types of awnings and different shade types work best on south facing windows, so it's always important to pay attention to the sun exposure and sun angles when recommending exterior shading. There's our windows. So moving on to floors and slab edge. Floor performance factors are really similar to ceilings because floor insulation is typically less than 12 inches tall. There's the main enclosure air barrier, usually the subfloor, which the insulation must be in contact with. And then there's the floor joists on each side of the insulation and front to back, which for some of the insulation will be the rim joist, which are technically part of the wall system and should be air sealed and insulated, like what we see in this photo where 1 part low expanding spray foam was used along with polyisocyanurate rigid foam board insulation. In the floor section, most of the heat loss is through the slab edge. Slab on grade is very typical in newer construction, and the slab edges are responsible for a tremendous amount of any heat loss. There's a number of ways to insulate the slab edge. You can do it on the exterior as a thermal break, and then also under the slab. In a building that will have radiant floors, you'll want a thermal break that goes down 18 inches and then continuous insulation underneath the slab. And a more typical way to insulate the slab edge is to use sheet rock wool insulation on the slab edge and protect it with cement board that gets painted. This provides the mechanical protection over the sheet rock wool. This is the slab edge treatment on the second case study home we'll be looking at in a little bit. This is a real picture of installed insulation. So type into the chat, is this a good installation or a bad installation? And I hope by this point you all recognize that this insulation will be providing no resistance to heat transfer. This insulation needs to be in contact with the subfloor, the joist, the band joist, in order for it to provide any benefit. To make the subfloor continuous and airtight, holes like around tub drains need to be addressed. This one here is sealed with extruded polystyrene and gun foam, which is a 1.1 part low expanding spray foam. This is a job in progress. These are R19 fiberglass bats being installed between the floor joists. R19 is a standard minimum building code value for floors. This style is often called sag and bag. Defects can often be seen where the insulation doesn't remain in contact with the subfloor air barrier. And then the insulation is typically significantly compressed at the edges. See the curvature? So that there's this compression at the edges that happens often with this type of installation. So here's another choice that's similar but different enough that it doesn't give us the same problems. This netting is installed at the bottom of the joist rather than in each individual joist bay. And so this creates a leveler surface, helping to eliminate the edge compression issue, and it provides the ability to fill the joist to full depth with the insulation, achieving a higher R value for the assembly. So these are R38 bats, twice as much value and installed better than those R19 bats in the previous picture. In retrofits, as we reduce the air leakage or air infiltration in the house, we almost always include a ground source vapor barrier on the soil of the crawl space. Most of the moisture that enters a home with a raised foundation comes out of the crawl space soil. So as we tighten a home, reducing the air leakage pathways, if we don't also reduce the amount of moisture entering a home, we may cause moisture problems in the home. So a vapor barrier on the soil will reduce the greatest source of indoor water vapor. And it provides a clean, nice work area to install mechanical equipment or to do any other work in the crawl space. This is a picture of a common defect found in two-story houses. This is a front porch that's attached to the attic, but it wasn't properly draft stopped between the attic and the exterior porch. The draft stopping should have been installed at the edge of the parallel cord floor trusses to separate what is a roof over the exterior versus the roof system over the conditioned space. So without draft stopping, the enclosure doesn't have a continuous primary air barrier, and outside air moves freely throughout the whole floor assembly. I mean, in a house with a continuous air barrier, there would be no need for insulation in the ceiling above the first floor, which is actually the floor system of the second floor, because the air barrier and the thermal boundary would be complete at the perimeter of the conditioned space. So there's our floors. Air sealing. According to the CEC's model, this is the biggest single heat loss component through the building enclosure. Infiltration is unconditioned air entering our homes and conditioned air leaking out of our homes. This is a huge variable when sizing heating and cooling equipment, and there's no way to know by looking at a house how leaky it actually is. In a most recent sample of tested homes, the tightest home in the sample tested at 2 ACH 50, so that's good. And the leakiest home in the sample tested at 32 ACH 50. That's a difference of 16 times more air leakage between one home and another built during the very same code cycle. In this picture, the bright wispy corona around this light fixture is what air leakage looks like in infrared with the blower door depressurizing this space. And the only way to know how leaky a house is and where some of those hidden leaks are is by using a blower door and an infrared camera. With these two tools, we can find where the true deficiencies are in the enclosure, like this problem wall. And then we can fix them rather than spending resources guessing and working on areas that are not contributing to the thermal and comfort issues of the home. This is the superintendent for Habitat for Humanity in Stockton, and he blower door tests all of the Habitat houses he builds. This is one of his blower door tests, 263 cubic feet per minute of air leakage at a pressure difference of 50 pascals, which calculates out to 2 ACH 50 for the volume of this house that we're testing. And most builders would be very jealous of this test, but he was disappointed by it. So on his next house, he worked harder and employed a different air sealing strategy. So since the majority of air leakage is through the ceiling assembly, he decided to do his first air infiltration test once the ceiling drywall was up and the wall between the house and the garage was all drywalled. With that air infiltration test, he achieved 176 CFM 50 before any insulation was installed and before any exterior wall drywall was installed. So at this point in the construction process, the house was at 1 ACH 50, which is equivalent to about 9 cubic feet per minute of air movement at natural, just without out any induced pressure. He accomplishes this by using joint tape and taping the ceiling drywall to all of the exterior and interior top plates in the entire building. Now, since he's the drywaller, he was able to ensure compliance with that approach. And at this rough stage of construction, he can then go around and test the enclosure to find every air leak and seal as tight as he wants to go. On the Mount Shasta triplex that I showed you earlier, that contractor used a different air sealing technique, which he just turned over completely to a crew of drywallers. And the specification he gave was they needed to glue the wall drywall in place everywhere it contacted a framing member. So if you look closely at this picture, you can see the bright white caulk that in place. It's where that's what glued every framing member to the drywall. So it glued every framing member for airtightness purposes. And then, of course, that the drywall is still screwed into place for structural purposes. But in terms of air leakage, gluing the drywall stops the air movement. And the main purpose of the instruction was to achieve a seal of the wall drywall to the top plates and to the bottom sill plates. The joint tape was used by drywallers. The joint tape used by drywallers seals the ceiling drywall to the wall drywall, but it doesn't seal the wall drywall to the top plates. And that's the location where we find the majority of the enclosure's diffuse leakage. And in each of these units, the blower door test average was 81 CFM 50 or 4 CFM natural. So those are two air sealing techniques that are fairly straightforward. Gluing the wall drywall, which is the airtight drywall approach, or sealing the drywall to the top plates. And they both yield universally great results. So two quick case studies. Because we have a great deal of data, we still talk about a home that was built in 2005 and monitored for a year. And the point I want to make today is the fourth bullet point down, that conventional insulation was installed. Looking at the specifications, we've got R21 fiberglass bats in the walls and R38 loose fill in the attic. That energy modeling would consider that to be completely conventional. And that's what was specified. That's what was installed. Nothing exceptional, no matter how you look at it, other than good installation quality with every bat cutted and fitted near perfectly. Also, back then, they didn't necessarily get carried away with air sealing there. So in this house, there was only minimal air sealing done. Excuse me. Every joint was not caulked, nor was the drywall sealed to the walls or to the top plates. All that was done was to install all the missing fire blocks. That was done by the contractor in charge of the energy features, which are the insulation and the mechanical systems. And he did this without any involvement of the framers or the builder. He took responsibility for this as part of his scope of work. The insulation installers cut and fit a foil-faced foam board where there were any missing fire stops. There's something, and this is just something that doesn't show up in the modeling or specifications, but by doing so, the contractor in charge of the energy features was able to reduce the blower door test number by about 50% of what a typically built similar house would have been tested at, just by assuring that they had a continuous and airtight air barrier. So they didn't change the specifications in any way, but the year-long monitoring showed that cooling costs were reduced by 81% and heating costs by 49%. And because this was a home being monitored, it was modeled using Building America's absolute best computer modeling software. And the software underpredicted the actual energy savings by 43% in cooling and 46% in heating. So there's just this horrible disparity between high performance and what shows up in the modeling, because things are presumed in the modeling that are not what is representative of the quality or lack of quality in real world installations. The second case study is a new home that was built in Redding, California by a contractor who knew what details to pay attention to. As a result, he built a high performance home. The home is all electric. Both water heating and space heating are done with heat pumps. Everything got monitored clear down to the circuit level. Each column is monthly energy usage, January through December. This builder chose the most immune to installation defect type of insulation for the walls and the attic, which, if you remember, is the spray applied cellulose. Each wall cavity was filled with the spray applied cellulose. A little moisture is added to activate the glue in the material, and each cavity is overfilled. This is a stud scrubber. It's used to scrub the excess insulation off of each cavity. It yields an insulation blanket that is about as near perfect as is possible. The exterior walls received R10 insulated sheathing, which is about double of what's prescribed by building code for exterior insulated walls. And he just ended up with a spectacular enclosure. The heating system was the smallest that could be purchased, but it still had too much capacity for this 2,372 square foot house. And the blower door result at the end was measured using a smaller fan since the house was so tight, and the final result was 0.52 ACH50, which exceeds our strictest air tightness standards. The house also had a balanced heat recovery ventilation system to provide continuous fresh air for the occupants. To get to a high performance home, we need to make the not particularly unusual choices that this builder made and pay attention to critical details of air sealing, properly installed insulation, and using good water heating and HVAC design and technologies. So a quick recap. California's building code has shown that new homes today should use about 9% of their energy for heating, cooling, and water heating, but the actual performance of homes being built has not achieved this metric. The energy modeling is seldom accurate, especially in light of the tremendous variation we see in insulation performance, enclosure air leakage, water heating, and HVAC performance. The lack of testing in the construction industry is something that the Energy Commission is trying to implement with HERS verifiers, but with little success, partially because HERS verifiers are only legally allowed to fail something if it doesn't meet the code minimum standards, which fall far short of high performance standards. And in addition, there's very little testing of the building enclosure. The majority of what HERS verifiers test are related to HVAC systems. And unfortunately, there's a huge difference between the passing requirements for what little testing we do see in residential buildings and what actual home performance can be. At this point, the HERS verifications are not working to provide homeowners with anything other than bare minimal comfort and minimal energy efficiency. Bid competition breeds an unverifiable sense of due diligence. Homeowners have been trained to get 3 bids from licensed contractors. What homeowners have not been educated in is how the attention to critical installation details matter, and that this standard of construction is not required by the state licensing board. So with this bidding process, contractors are trying to get the job based on how low they can bid it, rather than, kind of on a pride in workmanship and an understanding of their workmanship. So a few specific goals for air sealing and insulation performance. IR cameras, they no longer cost $40,000. They're like as little as $300 for little ones that can be used with your smartphone. Air sealing is really pretty simple. You find the air leaks and you fix them. And in retrofit, this is done by using the infrared camera in conjunction with the blower door. For air tightness in new construction, the performance metrics we want and are relatively easy to achieve are below 2 ACH50, target a maximum of 1 ACH50. We can do that in a typical stick-framed building in almost all cases. The average in new construction is more in the neighborhood of 4.5 ACH50 right now, but what we want is less than half that current leakage average. Some people would think that's hard, but once they set the goal and work to that goal, everyone finds that it's really fairly easy to accomplish. So to get down to 2 ACH50 is pretty straightforward and something that has been done over the years just by catching the big leaks. For insulation performance, now you know what the defects are. Find them, fix them, or install it well in the first place. We need about a 15-degree temperature difference across the assembly to do a good infrared scan. So sometimes that means in our mild climate that we need to do our scans early in the morning or run the heat or air conditioner all night so that we can achieve that temperature difference. On your current project, going back in and fixing a little defect that you find during your infrared scan might not be worthwhile, but as a training tool for the installers, showing them an infrared scan of their work, that's a great training opportunity for your next project. One contractor I know would do an infrared scan of an entire house with audio overdub, and his installers would watch it. And within 3 houses, his installers became basically zero defect insulation installers. So it's a very powerful tool for our installers. Just a couple of last notes. There are no silver bullets. There are 1,000 silver BBs, which are all the critical details that we must pay attention to in order to achieve high performance results. There's much more to learn about high performance buildings. And the next subject the series will tackle is heat pump fundamentals. So be sure to sign up for that class, which will be presented on April 25th. I want to thank you all for attending and participating. There is a 10-question quiz on the information presented today, so please take the time to test your knowledge and attend the rest of the High Performance Fundamentals series and earn your completion certificate.